Hello dear audiences, this is the part 3 of probability and statistics for engineering student, and I am Mohammad Momenzadeh, the person who presents this video. So at the beginning of this video we have a quick review of a thing that we discussed about it previously in a previous lecture. So we discussed about the histogram and frequency polygons and ogive graphs. So for the previous one we discussed about the different type of the graph and plotting that type of the graphs indeed, and we have the example over here that we actually plot the graph for this type of the class boundaries that you can see with the given frequencies. As I said it before, we can sketch that type of the graph. You can see over here the histogram and the polygon graph as well, and as you can see we connect the midpoints of the given histogram graph to make the polygon graph. So the important part of this discussion is the ogive graph that you can see over here. Since the value of the y-axis over here determines the cumulative frequencies, and as I said it before, for this cumulative frequency all the values will be increasing, and as you can see this graph is increasing as well. So it helps us to use this type of the graph to discuss about the probability as well. Later on you will learn how can we use this type of the graph to discuss about the probability. It's totally related to the probability, and it's a favorite type of the graph for most of the teacher in this course indeed. So we have one example. This is my favorite question for the first part of the discussion, and most of the time in a midterm exam I gave the student this type of the question. So let us consider this question clearly and find the value that is given over here. So let us discuss about it right now. So as you can see over here, we have the given frequency table. Some values are given and they ask you to find the other values related to this given information. So at the beginning we can see that the first frequency, the table, the first frequency over here is given by 2, and based on that one we have the relative frequency as 0.1. By these two information we can find the whole entire data that we can consider it for this table. Indeed, if we just take a look on it, the frequency table said that the frequency fi2 is equal to 0.1 in comparison with the relative frequency. Means that 0.1% or 10% indeed. 0.1 is equal to 10%. 0.1 means that 1 over 10, it's equal to 1 over 10, or 10% means that 10 over 100. It's equal to 10 over 100. Means that 10% of data are related to the first class. So with that information you can find the whole entire data that we have it over there. Means that 2 is related to 0.1, and if you just consider that one, means that we can make some proportion over here. 2 over x, the whole data, the comparison with the 2 with x is equal to 1 over 10 indeed. So by just calculating the x from this proportion, then you can find out that the x, the value of x over here is equal to 2 times 10 over 1, or 20. So the whole entire information that we have it in this table is 20. So I can fill this part as 29. Now means that the addition, the sum of all data is equal to 20. So the another information that we have it over here is 5 as well. The cumulative frequency is given at the second one is 5. Means that 2, the previous frequency 2 is added with the frequency of the second one and becomes 5. So the second frequency should be equal to 3. and also the cumulative frequency for the first one is as the same as the frequency, so it becomes 2, and cumulative relative frequency for the first one is as the same as a relative frequency, means that it's 0.1. so we just fill the value up to here. For the second one, we can calculate the relative frequency by dividing the frequency of that class, which is 3, by the whole space, means that the relative frequency over here is 3 over 20. 3 over 20, the relative frequency will be 3 over 20, or you can also simplify it and write it as a one decimal number over here, means that 0.15. we can write it as well as 0.15 for the relative frequency over here. And if we want to calculate the cumulative relative, you can divide this value, the cumulative frequency, by the whole space, or you can add the frequency of relative frequency of previous one by the next one to find it, means that you can add 0.1 by 0.15, the result will be 0.25, or you can simply divide 5 by 15. Both of them give you the same value, means that we can write that one as a 5 over 20, or we can also add 0.1 by 0.15. the result will be the same, so it will be 0.25. so this is the cumulative relative frequency for that part as well. For the next one, again, we don't have any information over here, so we'll leave it right now and we take a look at the relative frequency that is given in this part. So it's 0.4, means that 40% of the data just occupied this class. So 0.4 or 40% of 20 should be calculated. If we multiply 20 by 40%, or if we calculate that one, or multiply it by 0.4, or multiply it by 4%, then you will find out that the value that we have it over there is 8. So means that the information that we have it in this class is 8. So we can write over here 8 because it's 40% of 20. So by knowing that one, we can also fill the third class as well. 8 plus 2 is 10 and plus 3 is 13. So we need more information to reach 20. So it's gonna be 7 over here right now. So when you find the 7 as well, you can find the cumulative as well. You can add 5 by 7, which is 12, and then 12 plus 8 will be 20. Always, as I said it, the cumulative frequency of a last table should be as the same as the total sum. So right now you can easily find the relative frequency for the first one, which is 7 over 20. 7 over 20, and again you can add that relative frequency to previous one to find the value of cumulative relative frequency. At that case, means that 0.25 should be added by 7 over 20. And at the last step, for finding the cumulative relative frequency, we now always it should be equal to 1, because if you add this value, means that 0.25 plus 7 over 20 by 0.4, the result should be equal to 1, and at the end this one also should be equal to 1. We fill the blank places by using the given information in this way, so we calculate the value that is related to that one. So to discuss about the probability, it's necessary to understand some type of the definition. We start over here by talking about some definition of sample space and sample points. It's important to understand this type of the information and concept. Indeed, over here we have the sample space. The set of all possible outcomes is called the sample space. Means that when we have some type of the statistical experiment, when we toss a coin, when we roll a die, or do anything else related to the probability, we have a sample space. This sample space contains all possible outcomes. So it's a key over here, means that you should understand clearly that what is your sample space. When you want to talk about the probability, it's an important point over there to understand that what type of the thing should be considered as a sample space, as a point of a sample space. That elements of sample space is called the sample points, means that each of that outcomes in a sample space is called the elements or sample points of the sample space. Let me just give you an example. For instance, if we simply toss a coin over here, when we tossing a coin, the sample space contains two elements, H and T. This H determines the head and T determines the tail. So we have head and tail in that type of the sample space. Over here, the statistical experiment that we have, it is tossing a coin, and when we toss a coin, there is two possibility. If the coin is totally tossed very well and we have one side of a coin, we didn't consider the case that the coin is just dropped in a way that the head and tail is not obviously appear over there. So let me just show. So as you can see over here, we have a coin, and if you just consider the coin, let me just sketch a coin over here by using some circles. So it's a coin. The coin has two-sided. One side of that coin determined by the head, and the other side is called the tail, the part that has a shape. For instance, the shape of any person that the coin belongs to that region. Then let me just sketch one person over here. So this person determine the head, and we denote it by H, and the other side written the value of the coin, for example 2 euros. So this part of the coin is called by T. So when we toss a coin, there is two possibility. One possibility to get head and the another possibility to get tail. So because of that, the sample space, which contains all possible outcomes, should be considered as this S, or sample space, is equal. We just put a brace over here to determine the set, and in this set we put the head and tail. When we flipping a die, that die has six-sided. So if you just consider one cube over here, so I try to sketch a cube. So in each side of cube there is a number, for instance. Then we have 1, 2, for example 4, 3, 5 and 6 is on the other side. The side that you can look on it, if I consider the eye over here, so when we just take a look on that side of the coin, the die, then you can find a number. It can be 1 up to 6. So the set that contains all possible outcomes can be considered as a number 1 up to 6. These are the number that can be considered as an output, the possible outcomes of that one. So the another example over here is a case that experiment that we have tossing a die and then a coin simultaneously. So in this case, the result sample space can be obtained using the tree diagram. So what do I mean? Means that assume that we have one coin like this over here, and we have one die over here, and simultaneously in the same time, we toss the coin and then flip a die. So what is the result over there? So if we toss the coin at the beginning, means that we just use this coin at the beginning, then we have two cases, means that we have head or tail. So for the first one we have head or tail. This is the first outcomes that we can consider it. For the second step, after that we just toss the coin, we flip a die, and for the die we have 6 possible outcomes. So 1, 2, 3, 4, 5 and 6 means that we have a number 1 up to 6 over here. 2, 3, 4, 5 and 6. For the second one means that when we toss a coin and we get tail over there, Then again we flip a die and we have 1, 2, 3, 4, 5 and 6 over there. 4, 5 and 6 as the outcome, the second outcomes at the second step. So because of that, we can consider these things one by one. So the first one is head and 1. The first one that I just wrote it over here, 1H, means that we have 1 and H. We have 1 and T, means that the first coin is tail, and the number that is coming after that one is 1, so we have 1T. Then 2H means that we have this part of the diagram. This is a tree diagram that I talk about it. 2H and then 2T and then 3H, 3T, 4H, 4T up to 6H, 6T. So in the next step after that, we discuss about the preliminary topics on the set theory and talk about the union, intersection and the Venn diagram. Then after that step we discuss about the counting of the elements of a given set. It's an important thing. Indeed, we just try to skip from two important concepts in mathematics. The first concept that we have it over here is a set theory. In mathematics, I mean, it's especially about the mathematics, not about the probability or something related to that one. In mathematics, it's an important topic, the set theory. We cannot call any collection of the data as a set. It's more about the philosophy, and Bertrand Russell indeed discuss about that one, and we have indeed a lot of contradiction and interesting topics in around of the set theory. By itself, it's a branch of the mathematics. But over here, we didn't discuss about that things by the details. So we just need to know what is the meaning of the set over here, and we assume that we accept this concept to be a collection of elements. That's enough. I mean, it's enough to just consider the set as a collection of the elements. And over here, this collection of elements is called the sample space, and we denote it by the capital S, uppercase S. So the another topics in mathematics that we will discuss about it over here is combinatorics, and how can we count the elements of a given set. These two topics are too important in the beginning of the probability. If you understand these things, it means that you can solve any probability question. So it's important to understand the sample space. For this reason, you should understand the question clearly. You should understand that what we're gonna do on that type of the experiment. It's important to understand the elements of that sample space. We should understand the outcomes of the given experiment clearly. If you understand it, if you can assume the sample space clearly, then it's enough. I mean, you solve the question, you understand the question. But the most important thing over here is understanding the question clearly, and understand that how can we construct that type of the sample space. For the last example that we have it here, for the experiment of flipping two coins. Right now, if we flip two coins, I'm looking for the sample space that is constructed when we flipping two coins simultaneously. So over here, we have two cases. At the beginning, when we flip a coin, when we toss a coin over here, so assume that we have a coin over here, for example, that coin of €2 that I talk about it. So if we, this looks like a pound. So if we toss the first coin, we have two cases, the tail or head. And then for the next one, for the second coin as well, we have two cases. Again, we have tail or head. After that, we already toast the first coin. Over here, look over here, means that when we just write over there T, means that that type of the experiment has been already occurred over here. So we had a tail, and then after that one we have two cases, the tail and head for the second coin as well. For the second one as well, we have the same thing, means that head has been already appeared over there, and again we have tail and head. Right now all the cases can be considered as TT. This TT means that the first coin was tail and the second one is tail as well. The second case is TH, means that the first coin was T or tail, and the second one is head, and then we have HT and HH. So these are all the cases that I sketched the tree diagram to calculate it or determine it over here. As you can see, we have these cases, I mean HH, HT, TH, and TT. For three coins also we can do the same thing, means that this diagram is extended to one more branch as well, so we can write it for 3 branches as well and consider the 3 coins or 4 coins. Let me just sketch it over here. If we have 3 coins, this is for this first coin. If I just consider it here, this is the second coin, and for the third one again we can have TH and again TH for the second one here, and for the third one TH as well, and for the last one TH as well. Right now our sample space is extended to 8 cases, so you can write that 8 cases. To count the elements of this statistical experiment, we will discuss about it in a counting part in the next step, in the next part. So for this reason I can write it right now like this. TTT means that the first one is tail, the second one is tail, the third one is tail. Then TTH means that the first one is tail, the second one is tail, and the last one is H or head. So and so on. We have 8 cases right now. We can extend this tree diagram to sketch this type of the situation for 4 times of tossing or 5 times of tossing and so on. And as you can see, it's follow this formula that the number of a tossing, if it's considered by n, then 2 to the power of n determine all possible outcomes, the number of possible outcomes. Let us consider the next slide. So as I said it before, this type of the set theory is used to define some type of the concept in probability. Over here, all possible outcomes, as I said it, can be considered in one set that we call it the sample space. I denote it by one rectangle and put a name for that one. I write it over here S. This S is a universe set, or the big set, the biggest set that contains all possible outcomes. For instance, when we just tossing the coin, we have a tail and head. A single coin is tossed and 2 possible outcomes can be considered, the head and the tail, and these points are called the sample points. Right now, if I have a subset of this sample space, for example, this is a subset of sample space, and we denote that subset by one uppercase elements like A. Right now, A as a subset of a given sample space contains one element, which is T or the tail, and this set A, which is a subset of sample space, I use this notation to say that this set is a subset of S. Then this given set, which contains some elements inside of it, some possible outcomes, some of them, it can be all or it can be none as well. So this subset of S is called the event. So the event, as you can see over here, is a subset of a sample space. So for example, A is a subset of S. We can consider B as a set that contains 2 possible outcomes as well, means that H, for example, then this one is the another event that is a subset of S, and I can consider it over here. The another subset that I can assume it over here is a set that contains all elements, means that T and H, both of them. This is the sure event, means that for sure this event can be happen. So this T and H is a subset of S. As I said it, if it's as the same as S, means that there is no differences between S and C. It's a sample space by itself, but still it's a subset over there. And also we have another type of the set that we call it the empty set, and we denote it by phi. this phi contains nothing, means that contains nothing over here. In the brace we will not write even a comma or anything else. This type of the set is denoted by phi, and it's a subset of S as well. These are all possible for subset that we can consider it here. As I said, the H by itself is determined by B, and both of them determined by C, and the phi set is a set that contains nothing. So these are all the events over here, means that A, B, C, and even the phi set, which is impossible event, all of these things are the subset over there, and all of them are the events over there. So the another thing that we have it is a complementary set. The complementary of A denoted by A prime or A complementary, that we just use this symbol over there, and it contains all elements which is not inside of A. By the another word, the A complement or A prime, we denote the complementary set by these two notation, A complementary or A prime, and it's a set that contains all x's, such that we just use this demonstration, this type of the presentation for a given set. We put one vertical line over there to determine the property of the given x. It contains all x, such that this x is not belonging. It's not belonging is written with this symbol, means that we just use this symbol to determine that one. It's not belonging to the A. So this is the A prime or A complement. Always for determining the set we use this type of the notation. It's normally used in a set theory. So as I said it, when we want to use the this presentation, we write the name of a set, for example the set A, and then we denote that one. We write it by equal to, open the braces, and write over here the elements, the symbol of one element. Doesn't matter that x by itself belonging to that one, it's a symbol, it's a variable over here indeed. So this x, it contains all x, such that this line, as I said it, it's read by this word such that. We just use st, means that such that. So then we discuss about the property of x. For example, x is equal to even number, even numbers, even and x, and for sure x is belonging to the z, or x belonging to the n, natural numbers. So right now, by using this type of the notation, we can determine that set. So over here we have a set A. Again, I can rewrite A by the elements over here, because x is an element of n, or this set A is a subset of the natural numbers. And as you know from the high school, the natural numbers contains the elements as follow. It started from 1, 2, and going to 2, 3, 4, 5, 6, 7, and it's going up to the infinity. Means that these numbers are called the natural numbers. So if x is even and x belonging to n, means that that set of A is equal to 2, the first even number, then 4, then 6, and so on. For this so on, I just write a comma over here and put 3 dots, means that this type of the manner is continuously happen over there, and I just close the bracket. Instead of writing the elements of A by 2, 4, 6, 8, 10, and so on, all the even numbers and natural even numbers, I just use the notation that you can see at the top. So this is the another way to determine a set over there. So in the next step, after that we define the set, the events, we need to know some operation on sets. So these operations are the intersection and union as well. We discussed about the complementary of the set previously. Right now let us talk about the intersection. As the name is obvious, the intersection is a common element between two sets. And right now, when we discuss about the subset of a sample space, over here we have a sample space S. Indeed, this intersection is an intersection of two events. And as you can see, the A and B is mutually exclusive if there is no intersection between them. Means that the intersection of these two sets is equal to phi or empty. You can see these two separated sets. If two events are like this, means that they have no intersection, then we call them mutually exclusive or disjoint. These are disjoint events indeed, and we can shape this situation like this. The intersection symbols is like this, and we can say that A intersected by B or A the symbol B is equal to all elements like X. Again, let us write it by this notation and present it like this: all X such that X belongs to A and X belongs to B. This words and or is important here. We call it and over here. When we say that something is happen and the another thing is happen as well, means that both of them simultaneously in the same time should be happen. So X belongs to A and X belongs to B. In this case, we can say that A intersected by B is given by these values. As you can see over here, this is the common part between A and B, and we shaded over here, and you can see the intersection of two sets or two events. So the union of two sets, the another operation that we can consider assume it for the sets or the event is given by this shape, and the symbol of the union looks like a bowl that the elements will be going inside of that element. I mean, this can help you to memorize these symbols, the union symbols. And if we union A by B, means that we are looking for some set that contains, let me just open the braces, it contains all elements like X such that X belongs to A or X belongs to B. Right now you can determine the differences between and or. These two words is totally different. When we said that it's or, means that one of them gonna be happen, and it's enough to say that the X belongs to that set. If you just take a look at this point, for example, this sample points, and let me just call that sample points an X, as an X. This point belongs to A, but it's not belongs to B. But when we use the word or, then we can say that the X belongs to their union, because it's enough that X belongs to one of them. When we use the words or, this is the differences between them. But if we say that and X belongs to A and X belongs to B, then this specific elements X that I denoted over here is not belonging to their intersection, because it's only belonging to A. That means if we have or, then it's enough that one of them will be happen. But when we have and, that means it should be happen for both of the cases. This or is specified by the union, and this and specified by the intersection symbols. It's very important to understand these differences, especially when we discuss about the cases of the probability. When we have a statistical experiment and we said that something is happened or the another thing is happened, means that it's enough to one of them gonna be occurred. But when we use and word, then it's gonna be the intersection. I hope that you understand the differences between these two signs, and it's very essential to understand it, because otherwise you cannot distinguish between them and it's lead you to the wrong point. So if we have or, I emphasize about it again, if we have or, means that the first thing is happen or the second one is happen, it's enough one of them gonna be occurred, one of them gonna be appeared. But when we use and, both of them should be happen or both of them should be occurred, and the
the second one gonna be used. I mean, the intersection is used for and the union is used for or. So at the end of this lecture for today, we just have some relation over here that we need to verify them by using the Venn diagram. So at the beginning, let us discuss about the cases that we have it over here and calculate the value that we should consider it over here. The first one is A intersected by phi, means that if we have one set and we want to know that what is the intersection between A and empty phi. So the empty phi has no element, and the intersection of them means that the common elements between A and phi. So let me just write it over here. If we want to know what is A intersected by phi, so the result should be considered as all elements that the X belongs to A, and in the same time, it's important to understand it again, I emphasize about this one, and in the same time X belongs to the phi or the empty set. But we know that the phi is empty, there is no elements over there. So if X belongs to the empty set, means that X is nothing. So the only common elements between A and phi should be phi by itself, means that it contains nothing. None of the X's can be considered as a common element between A and phi. So the result over here is equal to phi. So if we want to verify this type of the things with the Venn diagram, in a Venn diagram we should sketch one universal set, universe set, that we denoted by S. And if we have a set over here like A, let me just consider A, and if we consider the phi is nothing, means that there is no elements inside of it. The common part between A and phi should be phi by itself. So this is the reason that the A intersected by phi is equal to phi as well. Let me just use a complete circle here if I can sketch it. So this is gonna be phi. Now the union of them, if I just change the intersection part to union, then I'm looking for the union of A and phi, and instead of the words that we put it over there as and, I should erase that one and put and instead of or. So if I have and, means that excuse me, we have the or here, so we have or here because it's union. When we just put or, means that we put both of these things in one bowl. It looks like that we have a bowl over here, we have one plate over here, and we put the elements of A inside of it, and we put the elements of phi also inside of that set. And when we put both of them in one plate or one bowl, then it's determined A union by phi. And as I said it, the A union by phi right now, it should be equal to A by itself, means that the union of both of them is equal to A. And if you just take a look over here, the phi inside of A give us the total A. So the result of A union by phi will be equal to A. So the another part of that question is calculating A intersected by A prime. And again, I just use that notation to show that what does it mean. If I want to just calculate the intersection of A and A prime, or the complementary one, means that I'm looking for all x's such that the x belongs to A, and simultaneously in the same time, and I should write and over here because it's an intersection, and x should belongs to A prime in the same time. So A belongs to A prime, I can repeat that one over here and rewrite it. Let me just rewrite that one here. So x belongs to A prime means that x is not belonging to A. So x belonging to A prime means that x it's not belonging to A. So it's impossible that the x belongs to A and in the same time x is not belonging to A. So all of these x's are empty set. There is no elements that we can consider it over here for their intersection. So the result of that one will be phi, and I will write phi over here to determine the result. And when we discuss about the union, the only differences that I should consider it over here, and it's make a lot of things changed, means that I should put or over here. So means that the x should belongs to A, or x is not belonging to A. If I assume all the elements of sample space, means that all S over here, then if I have y as an element in S or sample space, then there is two cases, there is two possibility. Then y belongs to A, or y is not belonging to A. By the another word, x belongs to A prime. There is two possibility for any elements. So as you can see over here, for each element there is two possibility. One is belonging to A, or x is not belonging to A. Because of that, the union of A and A prime is equal to S. We can determine this situation even by using the Venn diagram. Again, if I consider the universe set as S, and I assume the set A over here, and if I just color it by the blue, light blue, if I just color the A by light blue, then A prime will be the elements in over here. So the union of these two sets will be S by itself. So the result over here for A union by A prime is S. Right now, let us take a look at the next case that we have it over here. The next case said that what is S prime? And if you want to calculate the S prime means that it's contain all x's that this x such that x is belonging to S prime. This is the definition of S prime. And as you know, x belonging to S prime, it means that x should not belonging to S. Means that I can write it x is not belonging to S, but S contains all possible outcomes, and if x is not belonging to S, so the result should be empty. Means that there is no elements that cannot belonging to S, so the result over here will be phi. So for phi prime as well, we have the same situation. Means that if I want to know what is the meaning of the phi prime, means that it contains all x's such that the x is belonging to phi prime, and x belonging to phi prime means that x is not belonging to phi, but phi contains all empty elements. There is nothing inside of the phi, so x is not belonging to phi, means that it should belongs to S. So the phi prime is S. And over here we have the rules that shows the reflexibility of the complementary elements. So if you have A prime prime, this A prime prime will be A. So we can use the same techniques to discuss about the result. Means that we can say that okay, we have A prime here, A prime prime, so it means that it contains all x's such that the x is not belonging to, it's not belonging because of that prime, it's not belonging to A prime. So if x is not belonging to A prime, I can remove that prime and change the belonging sign to the negation of that element. Means that x belongs to A. So it means that I just remove that prime and change this belonging, not belonging, to the belonging case. So the result will be A. The last two things that we have it over here are the DeMorgan rules. So it said that if we just put the prime for whole, parentheses over there, it's changed the intersection to the union and the union to the intersection. I just show the case for the one of them, and the another one is as the same. So as you can see over here, we have the case of DeMorgan rule, and let us take a look on it. This is the intersection of two sets A and B. This is their intersection, the common part between them, and the complementary of that one is a part that is not include that common part, means that this shape determine the intersection 1 prime, means that it will be A intersected by P, B totally prime. So this is the complementary of their intersection. On the other side, this is A prime over here, that is included all the cases that is not inside of A, and this one is B prime as well. And the union over here, the union of A prime and B prime, means that the common part is a part that we have it over here. The only part which is not covered is a common part in this case. So it's going to be all parts except the common part, and as you can see, the A prime union by B prime is as the same as A intersected by B totally prime. So this somehow proved the DeMorgan rule by using the Venn diagram. So the last part of our discussion are our references. These are our references, and one more thing is about one applicable website. The website is Math is Fun. I want to introduce that one as well. So the Math is Fun. Let me just write it over here. The website that we have it is www.mathisfun.com. This is the good website that you can find the preliminary parts, and we use the concepts and some definition of that website for covering the union and intersection. I hope that you're interested in that in this lecture. Thank you for your attention.